So on the top, I will drop our transformation first. This is X, Y, and this is our Z, right? So we're going to now look at the torque in the X direction first, okay? So so we have to watch the direction of the torque when we're looking at this structure. So now I'm going to view our shaft, okay, from the plan view, okay. So we are going to look at X, and then we are going to look at Z, okay. So we are going to look from the top. So this is our shaft. Right. So this will be our element H. And over here will be our element K. And if we look at TX, okay, so this is where our TX is, right? If we look at TX, from the plan view, the TX look like this, right? If you use right-hand rule, right, you look at the top, it's going down that direction. If you use right-hand rule. Now, question for you. When you have a shaft, when under torsion, under rotation, when will the shaft break? Anyone? When will the shaft break due to torsion? Will it break during rotating, or will it break when you're trying to stop it? Anyone?
When you're trying to stop it.
Well done. Why? You're right. You are absolutely right. Have you broken a shaft before?
Yeah.
Where about you've broken your shaft? Tell me more.
I think it's at a 45-degree angle, right?
Yeah, but in real life, okay, I'm not talking about theory now. Okay, when do you have when have you broken your shaft?
Well, I was rotating a drill bit, and you know, and then it got stuck on something, and it just cracked in half.
There you go. Okay, when it's stuck, it breaks. When it's rotating, it will not break. That's a good experience. Can you hear that, right? So, i.e., again, same analogy. Okay, if I have a very strong heart, I jump from 5th floor, right? When will I die? Will I die on the 4th floor? No. Will I die on the 3rd? No. I will die on the 2nd? No. I will die on the ground floor because my motion has been resisted. Yes or no? Right? I cannot fall through the floor, so I absorb all the energy it hit me. Same thing. When the shaft is rotating, it will not break unless under fatigue. Okay, for this case, we're not going to consider fatigue. Okay, fatigue means cyclic loading. That will be under 3E. So when it will break, it will only break when we do this. So we are inducing a resistance. So now it's a built-in, right? It's a built-in. So this element at this side cannot move anymore. Okay, it can't move anymore. So based on how the structure will deform, okay, so we know this is, so the shear stress is equal to TR over J. Okay, right, with TR over J. So for this case, the deformation will be a twist. So at this point, right, this thing will want to come here. Yeah, bad drawing. Sorry, people. My badness. Okay, so the torsion, when you lock one side, it will want to move this way. Okay, so now your beam or your twist, So this is your twist. I think the angle is pi over here. So this is your twist now, right? Because you lock one end, the other end still want to rotate. Okay, so this is an angular motion. I draw it like a straight line because we are viewing from the plan view. So when that's the case, this point over here will come to here. Okay, so this point will come to here. And this is how the element is distorted. Okay, so this is how the element will be distorted. So when the element is distorted that way, okay, like what we have learned, so is it positive shear or negative shear? So I'll draw for you the difference. So positive shear, right? So this is your element. On positive shear, this is how your element. So this is positive shear configuration. So this is positive shear deformation. Okay. Then when you look at negative shear, right, the element goes opposite. So if you look at how our structure is deformed now, right, is it positive shear or negative shear? Anyone? It is what? So if you look at this pattern over here, right, this pattern I've drawn, maybe it's not very obvious. If you look at this pattern that I've drawn, okay, that I'm going over, it is known as what? So it's definitely not positive. So this is under what? Negative shear, right? Okay. So positive shear, there is. So you look at you look at this portion over here, it's the same, yes or no? Or the other end. So this is what we call negative shear. Now, if you design structures that are homogeneous or isotropic, same strength in all direction, you'll be fine. But if you are designing, you'll be fine in the terms where in terms of whether is it positive shear, negative shear, you don't really care. Okay. But if you are designing a shaft that is unidirectional strength, for example, carbon fiber, it is important to know whether is it positive or what negative shear. Okay. So now, if I were if based on the same orientation, same applied stress, right, and then we look at element, we look at this shaft now. So now we are viewing it from at the top at the plan view. We are viewing it from the wait, I'm now a bit, so this will be, wait, on to view from X and Y. Okay, so now I want to see X and Y, and this is my rotation about Z now. Okay, so you still see the same thing. All right, you still see the same thing. So now your element H is up here, and over here, this is your element K, right? And TZ is still coming down. So as I mentioned earlier, you only get stress when you resist motion, right? So that's where, if you look at how the element will deform, this part will want to come down here. This is how the element deform. So whether is it element H or element K, it is both going to be what? Negative shear. It will only become positive shear when what happened? Okay, it will only become positive shear. So element H and element K will have positive shear if the torque is in the opposite direction. So what do I mean by this? Okay, so let me elaborate. So now, again, it's been locked. Okay, this is our shaft. Now, TX go opposite. Okay, so the deformation will look like this now. Right, it wants to go this way now. Right, for either element H or element K. So when that's the case, if you look at deformation, this is then classified as what? Positive shear. Okay, so that's why when we design shaft with carbon fiber, it was meant to rotate in one direction only. If you reverse the direction, okay, the strength is no more the same. Okay, I repeat again, the stress is no more the same. Okay, so that is what you see when you design shafts. Okay, now, so we have been through bending moment. Okay, moment about Y, moment about Z. What we realize about moment about Y or moment about Z for this case, all our direction are in what? Stress X. Whether is it moment in Y or moment in Z, and then we have our what? Our shear. Okay, down we look at our shear. Now, always remember, based on this formula, right? So from based on TR or the shear stress, okay, tau max will occur when R is at the what? R max. Right? The radius is at the R max. Right? So if we have a shaft over here, right? The radius is equal to a value known as C. Right? So tau max, so therefore, tau max will occur when TC over what? J, where C is the maximum radius of the shaft. Okay, right? So in shear, the distribution is the maximum shear will occur what? Will occur at the surface. I repeat again, in terms of shear, in terms of shear induced by torsion, right? The maximum shear will occur where the radius is the what? Maximum. Okay. The shear force, it has a distribution, right? The distribution is at the surface is the smallest, right? This is interesting. Okay. So if I'm gonna sketch, okay, if I'm going to sketch now, so this is the radius, okay. Now this is the shaft, right? So now the shaft, right? Now that is our shaft, and then this is our center line, right? So based on here, I'll call this is where my element H is, and this is my element K is. Okay, so one is element H, the other one is my element K. So now we're going to look at what will happen when you have a what? When this is under what? This is under TX. Okay, this is under Tx, right? So the distortion, right? So the distortion, if this thing has been locked, element H will the point at element H will want to twist in this direction, yes or no? So this twist over here, like what